So, all right. So according to the Hadley model, and this is where I have a beef with kind of this material. It's called the single cell model. Now, to me, I see two cells there. I see a cell in the northern hemisphere and a cell in the southern hemisphere. So, just go with me, single cell model. Okay? So this is what Hadley said. You kind of see the hot spot around the equator, rising the tropopause, going both directions. So now the next one's a little more complicated, and I think to kind of present it, I'm just going to go ahead and click on this little video and have it kind of talk you through it, and then we'll add to it. The thing is there's actually 3 cells in each hemisphere. So they call it the 3-cell model, but I would call it the 6-cell model. So let me go ahead, and I've kind of done it here. Each cell is broken down. I have 30. You can write this in your notes if you want to. I have 30 degrees in each hemisphere, latitude, and I have 60 degrees each hemisphere, latitude, okay? So it's kind of broken into thirds. So we have Hadley cell, and then we have Ferrel cell, and actually that's us, part of the U.S., so that's us, not U.S., because part of the U.S. is actually in the Hadley cell, and then we have the polar cell in here. It gets pretty busy very fast. The reality of understanding these planetary winds, these macroscale winds, is kind of a 3-dimensional sort of thing I've already alluded to. Okay, it's not just the surface, not just twisting on the surface, moving on the surface, it's actually what's happening at upper elevations. So that's kind of what we need to kind of walk through to make these 3 cells. Okay, and then we have the Ferrel cell down here, and then we have the polar cell here. One more thing I want to add to this kind of basic thing before we move on is this, well, I guess I'll just, I'll leave it the way it is. Bless you.
Thank you.
Okay, so let's kind of see what this looks like. I'm going to be kind of using this on the board and kind of using this as the surface, and to kind of talk about upper winds, I'm going to kind of come up from the board. Okay, so here we go. So basically, our hot spot is usually around the equator. But like the video said, it's not always near the equator. Because we know that the hot spot in maxes out, let's see, June 21st or so, the summer solstice, you guys would tell me the hot spot is up here, and you're right. Okay, December 21st, you guys would tell me the hot spot's down here, and you're right. So that kind of hot spot, the middle of basically the pair of Hadley cells, migrates seasonally, and that's what she said on the video. Okay, so this is talking about the, this says basically this warm air rises, hits the tropopause, and it goes both directions. So part of it goes this way, and part of it goes this way, right? All right. So now, you see where we bump up against the next cell. So I went ahead and said 30 degrees south and 30 degrees north. So so let me go do this again. About 30 degrees north, this leg of air is going to go down. It's going to go down, okay? Literally, and there's proof of these 3 cells in each hemisphere, okay? So the air goes down. One of the things about descending air, okay, is it's going to be squished or compressed, and that's the opposite of adiabatic cooling. It's adiabatic warming. So honestly, here, where the end of the Hadley cell, the beginning of what we call the Ferrel cell, that descending warm air is dry and it's warm. Okay, so about 30 degrees latitude, or kind of where the Hadley and the Ferrel cell bump together, that's where we're sometimes kind of just find our deserts. Okay. Horse latitudes, the name horse latitudes. So horse latitudes then is kind of at the surface. Okay, go back to the surface. Here, the intersection of these 2 major cells. It got its name, quite honestly, and for you animal lovers, I apologize. It got its name because, like, if you are here-ish, you know, trying to get across the ocean to here, and you are in the horse latitudes, like the slide says, your wind, and you're using sail to get from point A to point B, there's not the wind for your sails at times. It's kind of seasonal, kind of a little bit hit and miss, okay? So if you run out of wind and you need to lighten your load, one of the things you can do to lighten your loads is to toss the horses overboard. I'm sorry, I know it's terrible. So part of me pictures about here, you have like, if you were to go down, you'd find like horse carcasses.
Oh.
I know, isn't that terrible? That's why they call them the horse latitudes. Okay, so let's talk. So we kind of have this couple of things going on. We have this wind, this air aloft, and remember I said aloft, basically we have at the tropopause, air going that way and air going that way. Then we have what's going on at the surface. So at the surface, okay, at the horse latitudes, where that, about 30 degrees in both hemispheres, where the air came down, it's going to splash and hit the earth, and it's going to go both directions. It's hitting the earth, and it's going both directions. Okay, Coriolis force. So it's hitting the earth, it's coming this way, well, how do I say? It's going towards the equator here, and it's going towards the pole here. Now, this one, do you guys buy this? That as it comes down, it's going to deflect to the right, okay? So here we go, coming down here, deflecting to the right. At the surface, that red line is the direction of the wind at the surface. It's actually at the surface, we call it, you know, we would call it an easterly wind.
Something like northwest winds.
That's something different.
Okay.
Yeah.
Okay.
I don't really can't address that right now. He asked about northwest winds, and that's kind of,
Okay.
these are planetary winds. Now, it's not to say you might have some small winds working in there, but I'm talking something you can sink your teeth into, something that Columbus, when he sailed the ocean blue, counted on. Okay? So these are actually what we call the NE, northeast, because they kind of come from the northeast, northeasterly trade. Trades or trade winds. At the surface, Okay, cool. Well, you could kind of do a similar thing and convince yourself if you wanted to. Let's see, how does that go? Let's switch hemispheres. Let's go into the southern hemisphere. So we have air rising here, hitting the tropopause, going down here, creating a horse latitudes about here, coming down, going in both directions. Let me grab my red pen. Now this is going to go, actually deflection is to the left in the southern hemisphere. So here we go. This part along the surface is going back towards the equator, so deflection is to the left. Okay. So actually, as I've drawn that red line, this is our southeasterly trades. Southeast trades, or trade winds, okay, at the surface. So those two red lines, okay, again, this is planetary large scale, those two red lines where they meet, okay, that actually is what we call, it's called the doldrums here. And the doldrums, if somebody says they're in the doldrums, they're like, So to me, the doldrums are kind of like the horse latitudes in that you really can't count on wind necessarily doing its thing. So they're called the doldrums, but it's also called, can you see where, I can't do this, where these guys are coming together, they're what we call converging, they're converging. Here in a minute, I have a slide that says, and I kind of ran out of room, I'm going to point right here, I'm going to call that the intertropical convergence, because the two things are converging, convergence zone, convergence zone. Abbreviated ITCZ. It almost sounds like something military, you know, it's like, sure there's a, okay. So that's kind of the two Hadley cells. Pair of Hadley cells, if you ask me, they just count them as like a 3-cell model, 3 cells in each hemisphere. Okay, so what about the ferrule cell? Well, what about the ferrule cell? Okay, so here at the horse latitudes, we had air coming down, going both ways. The air that's going actually towards the pole is deflected to the right, so grab your right hand. Okay, it's going to go towards the poles, deflected to the right. So actually here is where we get, in the ferrule cell, these actually are our westerlies. They're called, I call them mid-latitude westerlies. I guess I've been using black. Mid-latitude, ferrule cell, westerlies, because they're coming from the west. Again, these are surface winds. The other day, I told you, I don't know if you remember, but the other day, I told you at upper elevations, we have basically a west wind coming from the west at upper elevations. You could kind of convince yourself if you want to, but we end up with kind of a similar phenomenon here. Deflection is to the left, and so we end up here with another westerly wind in ferrocell in the southern hemisphere. Not so surprising. So it's very symmetrical, mid-latitude westerly. Very symmetrical. All right, so how does the ferrule cell end? Well, it ends about 60 degrees north latitude. Now, again, these are approximate, and just like the video said, these are going to migrate throughout the year. Okay, so the ferrule cell ends about 60 degrees, and what happens is basically the air along the surface bunches up, and it arises, it ascends. So actually we kind of have it's left a low pressure here at the surface. So air rises, hits the tropopause, and goes both ways. One leg finishes the ferrule cell, and the other leg starts or is part of the top cell, we call the polar cell. Okay. All right, oops, I must have got ahead of myself. Okay, polar cells. So, in order to address the polar cells, I like to kind of think of it a little bit backwards, not kind of coming from the equator or the intertropical convergence zone, but kind of coming from the poles. You guys told me warm air rises, cold air sinks. Okay, so if you kind of think, I almost think of it kind of breaking an egg, kind of like up here, and basically we have kind of air going that way at both poles. So with that in mind, let's kind of see how the Coriolis force would deflect it. So if it's going this way from the poles towards the equator, deflection's to the right, so it goes like this. So at the Earth's surface anyway, we have another easterly up at the poles. These are called the polar easterlies, and they're in both hemispheres. Now, all the things that I've drawn, easterlies, on this map, it's kind of ugly or whatever it is, and I've tried to explain it, is on the same map that you had the figure, okay, coming up. So, in Chapter 8, we're going to talk about air masses, and then Chapter 9, we'll finally talk about where air masses meet, we call the weather front. So we'll talk more about that, but actually here, at the surface, between these two cells in either hemisphere, we have clashing warm air and cold air. Okay, when warm air and cold air clash, that creates what we call a front. So actually right here, like the video said, this is a polar front, and this is a polar front. All right. So I kind of tease, not really, but I kind of tease, that this is a slide that I don't encourage you to like cut up your textbook, but you would like rip this out and put it on your refrigerator to get ready for one of the things on the unit exam. Okay. So take a picture of it. Okay, maybe that's a little cleaner. Okay. What's that?
We could copy it on our copy.
Yeah, copying. That's probably a better idea. Yeah, it's a little dramatic. I agree. So, but it has exactly what we talked about, okay? So if we have, and again, this hot spot migrates, but about the equinoxes, we just kind of passed an equinox, you figure the hot spot is supposed to be about the equator, okay? So the air goes up, and I like what your author's done. These little balls over here, these little things are kind of trying to show you what the air is doing off of the surface of the Earth. I think that's pretty cool. So it rises, hits the tropopause, and we said that the troposphere, topped by the tropopause, is thickest near the equator. And so actually this slide is consistent with what we talked about. And the troposphere is thinnest near the poles. So you see it hit, okay, it goes in both directions. Okay, it descends, okay, where you're going to have your two cells connect. Whoops, sorry. Where you're going to have your two cells connect, Hadley cell, ferrule cell. Okay, so it's all here. Cool. I misspell feral a lot. Sometimes I put one R, sometimes I put 2 L's, and I guess it's just one L. Okay. So this is our 3-cell model. Again, I apologize because I think it's really 6 cells, but 3-cell model. And here finally is what I put on the board. That hot spot that migrates, you know, we just passed an equinox. About during the equinoxes you would expect it to be near the equator. But then there's that delay of heating effect and cooling effect, you know, so that's called the Intertropical Convergence Zone, or the ITCZ. I think that's a cool name. So just to kind of emphasize a few things, these are the, let's see, let's pick on the northern hemisphere. So these trade winds, we would call them the northeasterly trades. We would call these the southeasterly trades or trade winds. It's the same thing. Don't you hate it when you take a course or something, they have more than one name for the thing? Well, they do. I call these the mid-latitude westerlies, same thing as westerlies. Okay, and they see them in both hemispheres. Polar easterlies at the top there. Also, though, it's not a small thing to remember that you guys told me that warm air will rise. Okay, well, let me pick a different color. Warm air will rise, and that actually creates a low here. Okay, here we have, and it's going to be a semi-permanent low. Here we have a semi-permanent high, where the Hadley and the feral cell butt up against each other, and we have a semi-permanent low up here, kind of that band where the feral and the polar cell bump up against each other. So kind of be familiar with that. Now I'll tell you that on your unit exam, I'm going to have to ask you some kind of questions about this model. And last semester, so I'll probably change it up a little bit, I actually had a map and had you guys say, kind of match up what was what. So we'll just see. You like the map? I don't know. I kind of like the map. Okay, so left and right here. Okay, on the right you see, well, I just showed, okay. But on the right it's more idealized. It's like basically ignoring the idea of large bodies of water, the oceans and the continents. So there on the left is more what it really does. But notice I qualify it down here at the bottom. Even this here on the left that says actual, on any given day, as you might imagine, this gets to kind of the small scale winds maybe, but on any given day, you can't assume that this is what it's going to look like. Maybe one of my goals here when I teach this class is for you to, when the weatherman gets the forecast wrong, for you to give him a break. I don't know, because it is complicated. It is very complicated. But hopefully you can kind of see the idealized and kind of the differences with the actual. The actual, like I said, takes into consideration the large bodies of water and land masses. Okay. So I think the video did a pretty good job, and we're going to revisit this in the slides, of talking about how that hot spot migrates. It migrates north to June, okay, and then from June to December it migrates south, the hot spot. And so I bet you guys buy this, and we're going to kind of actually have to think through this a little bit. But as your hot spot, or where your Hadley cells meet, your intertropical convergence zone, as it moves, everything else has to move. Okay? So it's actually what we're going to see. Yeah.
Can you go back?
I can't.
Oh, never mind. Go ahead.
Notice I got the feral with 2 L's here. I used to spell it with 1 R.
Thank you.
Mm-hmm. Okay. So macro scale winds, planetary scale winds, that's what we've been talking about with the Hadley cell and the feral cell and the polar cell, the 6-cell model, okay? Going back to this idea of a medium scale wind, a mesoscale wind, actually the mesoscale winds I want to talk about are created with these, like this band of semi-permanent highs here, this band of semi-permanent lows here. They create kind of some middle scale winds, okay? And we're going to take a look at those mesoscale winds. And we're going to see big H's and big L's. So I'll just remind you how that goes. I think you guys talked me through it before. Aside from this topic, if on a weather map, if you see an H, we're going to call that an anticyclone. And in the northern hemisphere, what direction does wind go? It deflects to the right, and it creates clockwise or counterclockwise around a high? Clockwise. Very good. It goes clockwise in the northern hemisphere. How about an L? We call it a cyclone. And L's which direction, clockwise or counterclockwise, do you think it should go by? Counterclockwise, exactly. Okay. In the northern hemisphere, and it's the opposite in the southern hemisphere. So let's see if that works for us. So.
Also low in the southern hemisphere would go clockwise?
Correct. So here we go, and actually I'm going to show you a pair of, here's the world, right? Look at the world. I'm going to show you a pair of these. The hot spot is this kind of bluish purple line here, the ITCZ. So hopefully you can kind of find that, kind of get yourself oriented, what must be where. So basically you have the Hadley cell right above that, okay, then you have the Ferrel cell above that, and the polar cell above that. Notice that this is in January. So in January, you expect the hot spot to be kind of in the southern hemisphere. I'm going to show you one in July here in a minute, and it is compared. Okay. Notice that the intertropical convergence zone does not go straight across. It kind of meanders. It kind of dips down over the land, and dips up normal over the oceans. So let's look at the northern hemisphere, and let's see if we can find this anticyclone-cyclone motion that we've been talking about. So let's just talk about the northern hemisphere. Let's pick this high. Now, do you see this high, and this high? There, I see three highs there. Blah, blah, blah. Mesoscale weather systems. What are they created from? They are created from this right here. They're semi-permanent, meaning they're kind of, it's like not always there, but they kind of come and go, semi-permanent. Have you heard of like the Bermuda Triangle, right? Okay, Bermuda, Azores High, okay, right here. So let's finish that thought. Highs, you told me, were clockwise. So those arrows there are showing you just generally how wind is flowing. Can you see the clockwise motion around the high? Clockwise motion around the high. These are mesoscale weather systems. Let's look at that one low up there. So can you see the counterclockwise around the low? And it also kind of reinforces another thing that we talked about. Those lines are all isobars. So look to kind of convince yourself. Pick on the low up there. Does it seem right? So if that's a middle low up here, okay, if that's a middle low up here, then we should, as we step out across those isobars, it should be getting higher and higher pressure. So I got 102, 105, 108, 111. Okay, so that is, I mean, that's kind of what we've been talking about. So there's January, and I actually have them side by side here in a minute, but compare January to July. In astronomy, one of the things that they did to find planets or to kind of understand distances to stars is use a blink comparator. They kind of go back and forth. So I'm going to do that. So this is July. This is January. July, January. Look at the Intertropical Convergence Zone move. July, January. Makes me dizzy. Oops. Okay. So anyway, July, it migrated north. Okay, you still see your semi-permanent high pressures. The low pressure up there went away. The southern hemisphere, do you guys remember what I said about water? Who has most water? The northern hemisphere or southern hemisphere? Southern hemisphere has more water. And actually, that's kind of a player in kind of some of these large-scale winds that we see. All right. Here they are side by side. One of my favorite headings in my notes is called The Wandering Intertropical Convergence Zone. It's almost poetic. But why does it wander? And it wanders because the Earth's axis of rotation is tilted and the Earth is orbiting the sun. That's why it wanders. So it's kind of back to kind of a Unit 1 thing. So this is just a image of the Earth that was taken from satellite, showing you kind of the chronic cloud cover that I was talking about. Where these, and the reason, again, intertropical convergence zone. What's converging there? Well, the two trade winds. That's why they call it the convergence zone. It lifts up, and as we know that air that's rising will expand and cool, and as it cools down, it can reach the dew point temperature. You know, this is all just kind of stuff we talked about. So, all right. Okay. So if you're like me, before I taught this class, I always thought, monsoon season, oh my gosh, that must mean that all heck is breaking loose, okay? But we're going to see that locations that experience monsoons actually have a crazy wet season and then a very dry season. So, you know, they have their calm monsoon season and they have their crazy wet monsoon seasons. But if a location exhibits that pair of monsoon seasons, that's because of actually, it's a seasonal thing, and I'll kind of show you how that works. So we have a pair, okay? They don't just bad and not good, but too much rain is bad and no rain is bad. So that's kind of what they have. And the two monsoon locations we're going to look at, the obvious one is in India, and the other not so obvious one maybe is actually in our southwest, has a pair of monsoon seasons. So what the monsoon seasons have in common is that due to the hot spot moving, or the hot spots moving, they get a new circulation that either causes you to be warm and dry, makes you be warm and wet, or dry and cold. All right, so here we go, starting with this one. Okay, find the purple line. So the purple line is the same purple line we saw before. The purple line is that intertropical convergence zone. The purple line is the hot spot, okay? And we're starting with India when they have their monsoon, their wet and warm season. So in their wet and warm season, what they have basically is the convergence zone is drawing in warm, moist air, okay, from the ocean. And it lifts up, or it smacks up against, remember we talked about orographic lifting? Orographic lifting. It smacks up against the Himalayan mountains and it rises. It's forced to rise.
And that's what causes the monsoons.
And that's what causes them to get dumped on with regard to precipitation. Yep, they get totally dumped on. Okay, so this would be their wet season. And you can see here, this is what we mean by wet, where actually over here, this, the way you read this bar graph down here is we have inches. So you know how we talk about, oh my gosh, we got 4 inches of rain, that's a lot of rain, blah, blah, blah. Well, we're talking like 120 inches of rain in the month. That is.
That's a lot of rain.
That is a lot of rain. And it's that warm, moist air seasonally coming up. A lot of rain.
It's like a 5 years worth of rain. Maybe not even.
That is a lot of rain. I agree. So if we compare that to this, now these maps are little excerpts of the maps we looked at before. If you go back a few slides when I kind of had the January, July, it's the same. If you look at this region of the world, that intertropical convergence zone drops down here. Okay, so now if you're living here on this side of the Himalayas, now you get a dry wind. Okay, basically. You don't have the orographic lifting going on at all. Okay, so now it's dry. Okay, so this is your dry, cold season. So one last thing before we go, let's take a look at here in North America. North American monsoon season. And when I was first teaching this, actually, you can Google, I think it might even be called, I don't know, but Google North America monsoon. Okay. So the one I want to show you, and when I did that, I came up with, I think it was Colorado. It's been a few years ago, but monsoon season in Colorado, I don't know. But the one I want to focus on is, like it says, kind of northwest Mexico and southwest U.S. Now this one works because land heats up more quickly than water. Okay, land heats up more quickly than water. So you guys told me the other day, since land heats up more quickly than water, if you have hot and cold air, okay, if you have hot air, is that going to be a low or a high pressure? Remember? Think of them kind of spread apart. Yep, they're spread apart. It makes a low. Cold air makes a high. Okay? So with that in mind, this is kind of what it looks like. Land heats up more quickly than large bodies of water. Land heats up more quickly. So actually, here in our southwest and in Mexico, we end up with, for a period of time, kind of an artificial low. And with that artificial low, then, what lows do is you have air coming into lows. Okay, so seasonally then, and by seasonally, you know, we're kind of seeing the bars for precipitation go up in July, August, September. That would be the monsoon season that's being described here. So seasonally, we have this warm, moist air coming in to that low, okay, and dumping in that region. So that's the monsoon season for our southwest. Good. Well, I think that's probably a good place to stop. But you can see the next slide, we're kind of switching gears from surface back up to winds aloft.
These classrooms so.
Try to keep them warm.
Yeah.
Don't know why.